inshallah شباب we will continue discussing the synchronous machine topics. Last class we discussed the derivation of the power and torque of the synchronous generator. يعني I will refresh your knowledge again. يعني firstly make the derivation. So we have the apparent power شباب S equals V multiplied by I conjugate, and we got the value of current from the equation EF equals V terminal plus IA multiplied by impedance Z, and we know Z has magnitude of ZS at angle theta S, and EF is magnitude EF at angle delta, or called power angle, and V terminal is the reference voltage at angle 0. So from here we can get current as E minus V over Z, and using angles and get the conjugate of angles, so we can multiply I conjugate by V to get this relation of S. To obtain the active power equation, the active power is nothing but cosine the angles, okay, magnitude multiplied by cosine the angle of the vector in order to get the real part of the apparent power. So this is our active power, and the sine part is the imaginary part, or reactive power. We agreed also in large synchronous machine we can neglect the value of armature resistance. So if we neglect the value of RA, the three-phase power can be V terminal EF over XS sine delta, and the reactive power could be 3V terminal EF over XS cosine delta minus 3V terminal square XS. طبعا يا شباب all of voltage values here are phases. تمام. So if it is, for instance, star connection, you have to get the phase value by dividing the line over square root of 3. طيب. And also طبعا for other equations, EF here, V terminal is phase, EF is phase, IA is phase as well. طيب. Also, we discussed that torque equals power over omega. So, شباب, there is an echo in the. If anybody open his mic, please, يعني turn it off. شباب. طيب. Okay. So, again, the torque equals power over speed. So we can say now torque equals P3 phase over omega. As you can see, شباب, you will find that this is the maximum value of torque multiplied by sine delta. Here as well, this is the maximum value of power multiplied by sine delta. So now we can represent the torque and power as a part of sine wave like that. However, there is a maximum value for the power. As you can see, maximum power here appeared at 90 degrees, and maximum torque as well. And for this part, I would like to discuss this part on the geometry of the machine in order to be understood. So if we have a شباب, for instance, this is the stator, and we have rotor here inside, and the x of the stator شباب, this is the stator x, and at the beginning the stator and rotor x were in phase, which means the angle delta شباب is the angle between stator and rotor x, which means if the stator, for instance, has N pole here, and the rotor, due to flux, fixed flux, has S pole like that, and the two poles are facing each other, so we can say here delta equals 0. So this means the شباب the motor is working at no load. طيب, if we now loaded this motor, so if we load the motor يا شباب, have an angle between stator and rotor axis. يعني now this is the rotor axis شباب. If we load the machine, the rotor will rotate like that, for instance, and this means S will move here. So now the angle between S and N is delta, and delta now is not 0. So here we have magnitude for delta. تمام يا شباب? So this angle now represents delta. This means that the flux line will move like that. And يعني, by the symmetry, we will have another pole here, N and S for the stator. So this is the flux lines now, شباب. As you can see, this is the base of the flux lines. Right. What will happen if the load increased more? If the load increased more, we will find that we have, and for instance, assuming the load is at 45 degrees like that. So delta here increased to 45. This is delta equal 45, and the flux lines will be stretched more. So the flux lines will be like that, moving from here to here, like that, and return back again like that. تمام? So if the power angle increase, the flux lines length will be increased. طيب, what about the flux lines يا شباب? Is it going to be stronger if the angle delta is small or high? يا شباب, what do you expect? Do we expect strong flux lines if it is long lines or short lines?
Short lines?
Short lines, exactly, because short lines means the two poles are very close to each other. So the machine flux will be strong enough. However, if you stretch the flux lines, this means that the flux will be weak. طيب, what will happen if we increase the the power angle to 90 degrees? Actually, if we increase the angle to 90 degrees like that, in this case, the flux lines will be very long, and it will be very weak, and also it will be cut. So if delta equals 90 degrees, delta equal 90 degrees, there will be something called machine loss of synchronism. Loss of synchronism means the flux lines are not exist anymore because of the big distance between stator and rotor poles, and in this case, شباب, the machine cannot work or load or carry the load anymore. So this is, شباب, the meaning of power angle now. For that, the point of maximum power here, we can call the point of maximum power as this point as maximum power. This is the first name at delta equal 90. We can say this is the point of maximum power, or maximum torque, or pull out power, or pull out torque. Pull out means maximum also, so it's either maximum or pull out. And also we call it يا شباب steady state stability limit. Because if the angle increased over 90 degrees or working in this area beyond 90 degrees, this area is called unstable region. So we cannot operate the machine at higher than the maximum power of 90 degrees. So these are the names شباب we used in our life regarding the point of maximum power. For that, we cannot increase the power or operate the machine at delta greater than 90. Okay. Now for the phasor diagram at constant power condition. يعني in order to recognize the phasor diagram here, يعني it's not easy to drive the phasor diagram while it's plotted like that. So let me draw the phasor diagram outside and observe what we need from this phasor diagram. If we have, شباب, the phasor diagram at lagging condition, so this is V terminal, and assume IA in the beginning is lagging like that. So this is IA, and JIAXS should be perpendicular to this vector. So neglecting RA شباب. Okay, so this is now JIAXS, يعني approximately 90 degrees, and finally this will be the vector of EF. شباب, is it clear? So here this is V terminal. Here this is V terminal. This is JIAXS. Assume this is IA case number 1, and this vector is EF case number 1. Now on this phasor diagram يا شباب, طبعا we know that this is angle delta. So this is delta 1 for EF1. For constant power operation شباب, you know the relation of power equal EF V terminal over XS sine delta. What are the variables that we can use to control the power? ها شباب, now if we have generator connected to an infinite bus and we would like to control the value of power, what are the variables that are accessible in order to control the delivered power? ها شباب.
The terminal voltage.
Terminal voltage, يعني for the synchronization يا شباب conditions we discussed, terminal voltage has to be the same as the grid. So if you would like to increase the power and you increase the voltage, it will disconnect it from the infinite bus. You cannot increase the voltage. Volt has to be the same as the infinite bus voltage. So you cannot increase or decrease V terminal. تمام? So V terminal is not accessible to control. It should be constant. XS is the machine parameter. It's constant as well. So we cannot control it. So now we have only sine delta and EF. طيب, according to the discussion now يا شباب, sine delta now, which is depending on the load condition, if the power is increased, the delta automatically will be increased. صح ولا غلط?
Yes.
So even delta, يعني delta can control the power value. However, you cannot have access to control it. It's automated control. You cannot control delta. it will be controlled automatically by the load itself. If the load increased, delta will be increased. If the load is decreased, delta will be decreased. However, EF here, you know the EMF relation, we can say EMF or EF equals 4.44 multiplied by flux multiplied by frequency multiplied by N per phase. صح يا شباب؟ دي الريليشن بتاعت الايه؟ EMF. So as you can see, we can control EMF by means of flux or frequency. However, we stated before, because the machine is connected to infinite bus, we cannot change the frequency or motor speed or generator speed, sorry. Okay, so in order to control EF now while the generator is connected to infinite bus, we can only control the field current. تمام يا شباب؟ For that, in any operation for synchronous machine connected to grid, we can or we have only access to control the field current of the machine in order to control EF. يعني, for instance, now we could see that power is proportional to EF multiplied by sine delta. So we can say EF1 sine delta 1 equals EF2 sine delta 2. For instance, we have certain operating condition for case number 1. Okay, the machine is excited and delta 1 due to certain load is known. If the load increased to delta 2, if the load increased to a value of delta 2, what we can do in order to keep the value of EF1 sine delta 1 equals to EF2 sine delta 2?
Change the current.
Change the field current, exactly. So we can change the excitation in order to keep power constant. تمام يا شباب؟ طيب يعني someone may ask, you said this relation is used for constant power. However, you confused us. You said now if the power increased. If the power increased, it's not constant anymore. Is it right? Actually, this relation is valid due at steady state يا شباب. At steady state, يعني, which means يعني anytime you can find generators at the power station, you can find that there is a demand for higher load. So it's expected to increase the how we can increase power. As we stated, شباب, the power will be demanded automatically due to the connected load. So when the load increase, the suddenly increase of the load leads to suddenly increase in delta. And in order to keep the power constant and avoid the reaching to maximum value of delta, we should increase the value of excitation. Okay, شباب? Again, now if you have suddenly connected load to a generator, the value of delta will be increased automatically. However, we need to protect the machine in order to avoid operation close to maximum or maximum value. تمام? So what we can do is to control the value of field in order to return to the same operating point again. Okay, شباب? For that, we assume that the new operating point is the value of maximum power. تمام يا شباب؟ يبقى يعني maximum power, sorry, the new operating point is the point of constant power. For that يا شباب, we use this relation at the constant power operation, which means at steady state. Steady state, which means there is no transient. The load is fixed now. طيب. For this phasor diagram يا شباب, if we have a load and the delta increased, assume that delta will be increased until the current being in phase with voltage, like that يا شباب. يعني current will be increased to reach to this value, And by the same way, GIAXS will be increased like that, and correspondingly, the EMF volt will be reduced because delta now is increased. تمام. So in order to keep the generator working properly, we should increase the value in excitation to return back again to the previous point. So this is the way, شباب, in order to keep delta as it is. So this is called constant power operation type. For now, if we would like to get the locus of E value in order to keep power constant, as you can see, شباب, this vector is EF. This is here EF2. This is EF2 due to IA2. تمام. The length of constant power, which is depend on EF sine delta for any of these curves or these vector diagrams, will be this vertical segment. يعني on this triangle يا شباب, the segment of EF sine delta will be this part. صح يا شباب? This part now represent EF sine delta, this length. So we can say the locus of EF constant, sorry, the locus of EF power is this line. يعني it means يا شباب, what's the meaning of locus? Locus means the vector EF will be changed on this line. So if the value if the excitation voltage EF changed across this line, this means that all of these operating conditions have the same power. Is it clear يا شباب? يعني for instance, if we have now lead power factor, or let's compare it for the two phasors now. Where is EF1 sine delta 1 يا شباب؟ ها? Is it the same as this length or not?
Yes.
طيب EF2 sine delta 2 will be the same value. صح?
Yes.
So we can say at this line, for any value of EF, the power will be constant. طيب let's draw the third case of lagging power factor. Leading power factor. So this is, for instance, another case for IA lead, okay, and GIAXS will be like that, and then EF will be this resultant vector. So for now, we can say that this is EF3, and the angle from here to here is the value of delta 3. So by the same way يا شباب, EF3 sine delta 3 will be the same vertical line. So here power is constant as well. طيب. For the current يا شباب, we have another relation for power. Power equals or proportional to IA the power factor. Is it right? And because V terminal is constant, so we can say power is proportional to IA multiplied by power factor. Power factor means cosine phi. So this is IA1 and this is the angle of phi 1. IA1 cosine phi 1 will be this line from here to here. صح يا شباب? So the segment, this segment here, from this point to that point represent the magnitude of constant power also. So we can say now the line of varying IA at constant power is this line. صح يا شباب؟ So this locus for IA between lagging, unity, and leading power factor in order to achieve the same condition, which is constant power. طيب, for this phasor diagram يا شباب, when delta or where the vector where delta will be 90 degrees, if I would like to draw EF now for delta equal 90 degrees. طبعا delta means this is the reference of delta, so 90 degrees means EF will be here like that. صح يا شباب? So this is here EF, which is considered as the minimum excitation. مظبوط يا شباب؟ يعني as you can see, value of EF, this is EF1 is high, EF2 lower, EF3 lower. Or the lowest value of EF will be the value at delta equal 90. So we can, or we could also observe here at delta equal 90 degrees, which means at this case, you will find the excitation minimum. So if we say the شباب minimum excitation at constant power operation, this means the angle delta is 90 degrees. طيب, again, comparing يا شباب the operation also for constant power, we have IA1, IA2, and IA3 here. What is the minimum value of IA? يا شباب,
delta equal to 0.
At delta equal to 0, which is
Unity. At
sorry, phi,
unity power factor.
sorry, phi equals 0, not delta. Is
Yeah,
it right?
Phi. Yeah.
Phi equals 0. You are right. So this means that if we said minimum armature current, this leads to you have unity power factor. صح ولا غلط شباب? So from phasor diagram here, we could observe many things. We could observe the locus of EF and IA. We could observe that at delta equal 90 degrees, we have minimum excitation, okay, and the minimum current achieved or obtained when the power is unity. تمام؟ طيب. Now we drive together the phasor diagram. Let's see in the slides here now. I think now it's clear here. We have three cases, EF1, EF2, EF3, like that. And the minimum value, as we discussed, it's here. طبعا we said before, the over-excitation after the unity power factor, okay? And the below the unity power factor is under excitation, تمام? And this value here, VE multiplied by X over V, and if you get the relation of power, we said power equal V terminal EF over XS sine delta. So P multiplied by X over V is nothing but EF sine delta. So this means EF sine delta. So this is the constant value of EF sine delta. تمام? And the same is also شباب here for VA, for the current multiplied by power factor. تمام? P over V is nothing but I multiplied by power factor. So these are the A conditions we used here for constant power, and the relation that we can use at constant power operation, EF1 sine delta 1 EF sine delta 2, and IA1 cosine phi 1 equals IA2 cosine phi 2. طبعا cosine phi or power factor. Right. Let's see this numerical example. We have here 3-phase 5 kVA, so 5 kVA, this is the apparent power of the machine, the rated apparent power, so this is S rated. 208 volt, this is the line-to-line volt, 4 poles, 60 hertz, star-connected synchronous machine, has negligible stator winding resistance and a synchronous reactance of 8 ohms per phase. So RA is neglected and XS equals 8 ohms. At rated terminal voltage, the machine is firstly operated as a generator. So the machine is working as a generator in parallel with, طبعا it has to be the same value of the supply voltage and the frequency. Otherwise, we cannot connect the machine. Right. Number A, determine the excitation voltage and the power angle. So we need to calculate excitation voltage, which is EF, power angle, which is delta, when the machine is delivering rated kVA, which is the 5 kilovolt ampere, at 0.8 power factor lagging, and draw the phasor diagram for this condition. طبعا simply يا شباب, we can start. In order to calculate EF, we need firstly to get the current. تمام. طبعا it's stated here we are working at rated kVA, so we can use the S rated and get the input current. So we can say, sorry, the generated current. We can say IA rated equals over square root of 3. So this is, شباب, now value of IA. And it's given also the power factor is 0.8. So we can say phi equal cosine inverse 0.8, which is here minus 36 because it's lagging power factor. But now we have the current magnitude and angle. So simply we can substitute in the relation EF equals V terminal plus JIA XS. طبعا XS is given 8 ohm and we got the current, so we can say now V terminal is equal what, شباب? In this relation
208
208 is line volt, is it right?
over root 3.
So we have to divide over square root of 3 angle 0 plus J XS equal 8 multiplied by current. Current here is 13.9 at angle minus 36.8 or 0.9.
Doctor,
So-
if it was delta connection, we will not divide by root 3, right?
Right, but the current in this case, is it going to be the same? Is it
No.
going to be calculated? Right, for that, يعني you يعني by the end of problem you will know that this is activity number 5. يعني you should prepare for it inshallah to be submitted in the next class. Right. So now we could calculate the value of EF. And firstly, يا شباب, before we calculating numbers, what is the expectation for the power angle delta? Is it going to be positive or negative? ها شباب.
Positive.
Exactly. We said before in the phasor diagram of generator. For generator يا شباب, delta all of time is positive. تمام. So when you substitute, you are sure that the value of delta will be positive value. طبعا here after calculation we could find that EF equals 206.9 at angle 25.5 degree volt. So this is now the amount of a excitation voltage, and the power angle is 25.5. Right. This is number A. Number B يا شباب, if the field excitation current is now increased by increased compared to part A, so we increase the excitation voltage, what do you expect? What will happen to the power angle? يعني according to the phasor diagram here.
It will increase.
So we expect when we increase the excitation, is it stated increase or decrease?
Decrease.
Increase. Increase.
okay.
Increased by 20%. So increasing excitation, and so we are moving in this direction. Okay, so we expect to have lower value of power angle. تمام. So here, if the field increased by 20% without changing the prime mover power, which means power is constant, find the stator current, power factor, and rated KVA supplied by the machine. طبعا يا شباب بس for part A we forgot to draw the phasor diagram. طبعا phasor diagram we plotted the phasor diagram many times, and also يعني I didn't add it here in the problem. However, plot the phasor diagram as we made, and should يا شباب made يعني to scale, sorry, not to scale but not freehand. Okay, يعني like what we have made in the Word file like that. طبعا the first case here represented the lagging one. تمام. So here we need to calculate the current, the power factor, and reactive power where the excitation is increased by 20%. طبعا يا شباب excitation increased by 20% and the power is constant. So firstly we can say the excitation increased by 20%. So EF prime for the second case equals to 1.2 multiplied by the first EMF. So this is the value. So EF now is increased. We expect, as we discussed, delta will be decreased. طبعا we should substitute now in the relation EF sine delta equals EF prime sine delta prime, and from here we can get the value of delta prime. As you can see, delta decreased to 21. It was 25.5, now decreased to 21. Fine. The corresponding current, how we can obtain the current? طبعا simple يا شباب. We have now the value of EF, the new value of EF, and its angle 21. So we can substitute in the relation and give the value of armature current. Now the armature current is 17.86 at angle minus 51.5. If you would like to calculate the reactive power now, يعني you can calculate it using two different ways شباب. Either saying Q equals EF the internal over XS sine, cosine delta minus V terminal square over XS. This is first way, or using the relation of three-phase reactive power for any source, which is طبعا شباب this is يعني multiplied by ايه 3 phase, it should be multiplied by 3 for the for any three-phase source. 3 multiplied by V terminal as phase طبعا multiplied by I A multiplied by sine angle phi. تمام. يعني here we calculate it as a function of 3 VI sine phi, and we could find that the reactive power is 5.03 k var. Okay شباب. Number C, with the field current as in A. So now we will return to operate the machine at the condition of part A with the same value of excitation voltage. The prime mover power is slowly increased. So the power will be increased now. What is the steady state or static stability limit? This is a theoretical question. It's not no need for equations or like that. You can just write the angle طبعا at steady state stability limit is the limit where the power angle is 90 degrees. So the answer of this question is the steady state stability limit is the operation at delta equal 90. Then what are the corresponding values of the stator or armature current, power factor, reactive power at this power transfer condition, this maximum power transfer condition. So now we have EF as in part A, however, delta is 90 degrees. From these data, we need to calculate IA, power factor, and reactive power. So by the same way, يا شباب, at delta equal 90, we can now calculate the value of power. So power maximum equals 3EF V terminal over XS. This is the value of maximum power. And also we can calculate IA. It's equal to EF, the same value in part A, but the angle is 90 degrees, minus 120 over angle 0. This is V terminal over JXS. As you can see, يا شباب, here the power factor is leading. Is it right? Is it logic or not, يا شباب? ها شباب?
Yes.
It's logic because as we described in the phasor diagram, here, can you see the at angle delta, this is E and this is JIA, so we expect IA to be like that, so it has to be lead. تمام? So maximum power will attain all of time for generator at leading power factor. طيب طبعا يا شباب, we shouldn't operate the machine at maximum power. We only investigate the parameters or values at maximum power to avoid operating the machine at this value. Okay. So we could get the value of stator current and the power factor by the same way. So activity number 5, شباب, inshallah, it's required from your side to solve the same problem at when the connection of the machine is delta. تمام يا شباب؟ Synchronous motor. يعني I will just discuss few slides, few يعني we have only 2-3 minutes maximum. يعني I will discuss the concept and يعني next class we will continue. Synchronous motor. طبعا يا شباب, the difference between synchronous motor and generator is only the power flow. يعني the current here will be coming from the supply to the motor. So we have input current, not output current. تمام? So we have the same equivalent circuit. The current is going to be inside the motor. So the equivalent circuit like that are JX and EF. However, current now is entering the machine. And this is V terminal. RA, JXS. So we can say now, شباب, EF equals V terminal minus IA multiplied by RA plus JXS. So this is now the relation of synchronous motor. Type, firstly, for the synchronous motor, we discussed that we have different types of motor. We have DC motor, we have induction motor, we have synchronous motor, and some other special motors. For synchronous motor, the machine is not a self-starting motor. What's the meaning of self-starting? Yani for DC motor, when you connect the supply to the motor will start rotation, it will move. However, in synchronous motor, the motor itself is not a self-start motor. Three-phase induction motor is a self-start motor. Single-phase induction motor is not a self-start motor. We need something also to make starting for single-phase induction. Similarly for synchronous motor. Synchronous motor is not a self-start. Yani when we connect the supply of three-phase to the stator windings, along with applying the DC supply to field, you will find that the shaft will oscillate and the machine will not rotate. Why this happened يا شباب؟ Let's discuss it clearly here. If we have the section of the motor like that, we have, due to three-phase supply, we have stator rotating flux N and S at a certain time, at t equals 0. And the rotor, for instance, was in this position. So for now, يا شباب, the pole N will attract the pole S of the rotor. Is it right? In order to reduce the strength, the length of the flux lines. يعني flux lines are moving like that. In order to reduce the flux lines, the rotor would like to move in this direction in order to make the flux lines as short as possible. If the motor or rotor start in the motion, the polarity of N here will be changed. Why? Because in the geometry of the machine, N will have here S, then N, then S, and so on. Okay? And when you rotate this flux, this N will move and the S pole will come instead of it. So which means that the N will be changed to S very fast. So if the rotor start moving to be attracted to N, the polarity of N will be changed to S. So it will start to be moving in the other direction. Okay? So based on that, شباب, due to the high change or high speed of the rotating magnetic field, there will be sometimes attraction, sometimes repulsion, and the rotor will not be attracted or will not be rotated. It will stay as it is with some vibrations. So what we can do to operate the motor يا شباب? And let's think together. What we can do now? Now we understood that the reason behind the motor, the standstill motor or motor not starting, is the high speed of changing the poles of stator, the high speed of the rotating magnetic field. So how we can start the motor يا شباب؟
Reduce the speed.
This is one solution to reduce the speed. And if we reduce the speed, this will allow the pole here, pole S, to be attracted to N. And if the poles change after that, which means N will travel, it will take pole S with it, which means the rotor will start motion. So this is one of the solutions, is to reduce the rotation of magnetic field. طب how we can يا شباب change the rotation or speed or synchronous speed? How we can reduce it?
Change the frequency.
Exactly. We have NS equals 120 frequency over number of poles. So this means that if we start with reduced frequency, the synchronous speed will be slow, and in this case, the stator poles will catch the rotor pole and start moving. Once the machine starts moving, you can increase the frequency. It will not stop again. It will continue in rotation. طيب, يعني decreasing the frequency, this is the right solution. And we can say if the frequency is decreased, we can assume that the relative speed between the two systems decreased. طبعا in the beginning, the rotor speed was 0. And the stator flux speed is synchronous speed. So the relative speed is the same as synchronous speed. تمام يا شباب؟ طيب. We have another solution, which is starting the machine firstly as an induction motor. تمام؟ However, I think this needs more discussion, and we can inshallah discuss in details in the next class. Is there any question يا شباب؟
يعطيك العافية دكتور.
الله يعافيك. اوكي يا شباب، ان شاء الله نراكم الكلاس القادم.